In this video, we will continue our discussion on transaction processing. We will basically look at the concepts of transaction and system concepts and how the transactions are scheduled in a database management system. So the DBMS must keep track of where a transaction starts and then where it terminates, and then it also needs to keep track of when the transactions have to be committed, that is saved to the database, and if the operations need to be aborted, then there's an abort action. So basically there's commands like a begin transaction, an end transaction to start and end the transaction, and then there's commit and roll back or abort. And when a transaction is aborted, what that means is whatever operations have been performed so far, all of those actions have to be rolled back, and the system needs to be taken back to the previous consistent state. And then in addition to that, there are the read and write operations with the database elements. So here's a state transition diagram that illustrates the different states in which the DBMS, a particular transaction can be in at any point of time. So our starting state is the when the transaction begins, it is in an active state where there's read and write operations happening. So that's the reason one of the states or one of the nodes in this state transition diagram is the active node. And some of the actions that can happen on it are read or write, and that will still keep the transaction in an active state. From an active state, if the end transaction command is submitted, then it goes into a partially committed state, and then the final commit happens, and from there it goes into the committed state. Once the commit has happened, then the transaction is terminated, and that's kind of the last state in this state diagram. Now it's possible that the transaction can be aborted at any point of time. So say the transaction is in active state and for some reason it's aborted, then that takes the transaction into a failed state, and from there it's terminated. Now abort can happen on partially committed state as well. So the same thing, it goes to failed, and then from there it goes into the terminated state. So that's how the transactions work. Now along with this, we also need a system log. Basically it's a way to keep track of everything that's happening in the database. All of the transaction operations are logged into it in a sequential manner. It's basically typically a file that's an append only file, and every operation that happens, there's a note in the system log that's appended to the end of the file. The purpose of doing this is so that in case of failures, it could be any kind of a catastrophic failure, an abort action, anything except for a disk failure, because if the disk itself fails, then we lose the system log. If for any of the other failures, basically what can be done is the log can be referred, and all of the previous so basically we can take the DBMS back to the previous consistent state using the entries in the system log. There's also a log buffer, so that relies on the main memory buffer that's there, and whenever it's full, basically whatever is in the buffer is then appended to the end of the log on the disk. So what's happening is this buffer is being used as a temporary storage space, and that's where all of these system log entries are going in until it gets full, and when it gets full, it gets committed onto the disk. And then the log file is also backed up periodically, because we rely on the log file for recovery in case of any kind of failures, and this log file is now making undo and redo operations possible. So the commit point of a transaction, so whenever commit happens, basically the idea is all of the operations have been successfully completed, and so they're finally written or saved to the database. And on the other hand, if any kind of failure occurs while a transaction is doing is performing its operations, then in the system log there will be an entry for start transaction, but there may not be an entry for commit record, which is the final action, and that indicates that there has been a failure. So all of the actions up until the start, going backwards up until start transaction, can then be rolled back. That is, we basically undo all of those operations to make sure that the database is back to a consistent state. So that's the idea of the commit points. Now, there are some desirable properties for transactions, and they're popularly known as ACID properties. And typically, whenever we talk of a DBMS system, we talk of these ACID properties and the ability to have transaction processing to make sure the ACID properties are maintained. So the ACID stands for atomicity, consistency and preservation, isolation, and durability or permanency. So basically, atomicity means that each transaction that's being performed, it has to be completely performed. The entire transaction has to be performed, or nothing should be performed, which means that that's the reason we roll back. So it's basically an atomic transaction, which has to be performed as the whole unit as a whole has to be performed. Consistency preservation is basically ensuring that the database is taken from one consistent state to another consistent state. And that's the idea of consistency preservation. Isolation is where we don't want any of the transactions interfering with each other, so each transaction must happen in isolation from the other ones that may be happening concurrently. Durability or permanency is basically the property that the changes must be persisted to the database correctly. So these are the ACID properties of transactions. Next, we'll look at how we characterize a schedule. So basically, how do we come up with a schedule when there are multiple transactions? And one way to do this is based on recoverability. So the focus here is that the ability to recover from any failures. So in this case, basically we look at the order of execution of operations from all of the transactions, and based on that order, the operations are interleaved in the schedule. So a schedule is set up so that there's interleaving of operations, so what that means is that order needs to be maintained. So that's one way to do it. There could be conflicting operations though whenever there is interleaving. So what a conflicting operation basically is when these operations belong to two different transactions. So there's multiple transactions and there are operations in each of them, and say those operations are accessing the same item X, and at least one of them is writing to X, then that's called conflicting operations. And in that case, the scheduling needs to be done more carefully, and their order needs to be determined more carefully. So what might happen is these two operations, they might, if they are executed, and if their order is changed, then the results or the final outcome might be different. So that's the issue, and we may not have a consistent database state. So there could be a read-write conflict or a write-write conflict, and those are the kind of things we want to avoid. So when recoverability is one of the goals, so basically we want to ensure that we are able to recover if in case of failures, and the DBMS should anyways not permit non-recoverable schedules. The schedules should be such that recovery is possible. The schedules should be set up in such a way that if a transaction is committed, then there should be no need to roll back. So which means all of the operations happen in the correct order, maintaining all of the asset properties, so there should be no need to roll back. Whereas if there's an uncommitted transaction, and in case of some issues, then those we should have the ability to roll back those. And sometimes there may be a need for cascading rollback in some of the recoverable schedules. So now cascade-less schedule. So coming up with a schedule where we avoid cascading rollback is one way to do it. Or one could go with a strict schedule where the transactions can neither read nor write an item X until the previous transaction, or the last transaction that wrote to that same database element, has committed, as in it has completed all of its operations, or it has aborted. So that's a strict schedule. And then with a strict schedule, there's an easier, simpler recovery process, because then it's easy to just restore the previous image. Now another way to characterize schedules is based on their serializability, if the schedules are serializable or not. And this is basically always considered to be correct when there are concurrent transactions are executing. So it's important to look at serializability when there's concurrent transactions, and there could be multiple ways in which these simultaneous transactions could be placed in a series. Maybe we say execute transaction T1 first and then T2, or vice versa. So this figure here shows the different possible schedules. The first one is where all of the operations of T1 are executed first and then T2, and remember, these are all happening they're serializable, so it's happening in a serial fashion. Now the second schedule is where T2 is executed first, followed by T1. In schedule C, we have interleaving, so it's non-serial. We have a few operations of T1 followed by a few operations of T2, again followed by a few operations of T1 and then T2, and so on. And then in a similar manner, schedule D also is non-serial, and there's interleaving of operations. Now the problem with serial schedules is that there is a limit on concurrency, because it's the moment there is interleaving, there's only one transaction that's being executed at the same time, so that's limiting in a lot of ways, and it could slow down the performance as well, and that's the reason in most cases this is unacceptable in practice. And the but then at the same time, whenever there's conflicting schedules, we have to deal with it, and there may be a need to go with the serial schedules to make sure that all of the database elements are intact and consistent. Now there's also the concept of equivalent schedules, where the two schedules are equivalent. Now if they produce the same final state of the database, now that just because they produce the same state, it doesn't mean they are equivalent, because producing the same state could be accidental, as shown in this figure, where there's the first serial operation with three operations. We're reading an item X, adding 10 to it, and writing X. Now S2 on the other hand is reading X, and then to X it's multiplying 1.1 and then writing X. Now in this case, it so happens that the output or the final state is the same, but that doesn't mean that these are equivalent schedules, but because you see the operations specifically are not the same. So basically there is this concept of conflict equivalence, wherein when we are looking for equivalence, we basically focus on the conflicting operations, on the two conflicting operations that are that are there in the schedules, and if their relative order is the same in both the schedules, then that's called a conflict equivalence. So here's a procedure by which one could test for a serializability of a schedule. So basically, for every transaction TI that's participating in a schedule S, we create a node and label it as a TI, and we kind of create a precedence graph uh, to basically see the precedence of operations. And then say there's another transaction TJ, and depending on what items they are reading or writing from, a precedence graph is created. So as you can see here in this figure, the first one is basically a serial schedule where transaction T1 is first reads X, or does some operation on X, followed by T2. So that's a serial schedule. B is also a serial schedule. Now the way to find out that something's not serializable is by if there are cycles in this precedence graph, like you can see in the third one in number C. So that's how by creating these precedence graphs and looking for cycles, we can determine if it's serializable, or if it's a serializable schedule or not. So the way it's used in concurrency control is basically creating a serializable schedule, thereby concurrent execution is possible, and we are not giving up on the correctness. In practice, it's very difficult to test for serializability, but then the database management system enforces a number of protocols, basically rules that ensure the serializability. So you'll see that SQL provides transaction support. In SQL, there is no explicit begin transaction statement, but then there is an explicit end transaction, and there is explicit commit and rollback statements. And then the way one accesses the database elements is either a read-only or a read-write. Those are the two kinds of access modes available. So basically, there is different database management systems have different kinds of transaction support, and basically this is what's available in SQL. So to summarize, we discussed transaction processing by starting out and discussing single and multi-user database transactions, and the need to handle these logical units of database operations called transactions, and how there could be concurrent transactions which need to be executed more carefully, and need to be scheduled more carefully. So we saw the concepts of system log and failure recovery, what happens on failure and how we recover from the failure. We looked at the concepts of committing transactions, and how the system log can keep track of all of the operations, so that in case of failure, it will facilitate the rollback process and takes the database back to its previous consistent state. Then we looked at scheduling and how the scheduling happens. It could be based on recoverability, or it could be based on serializability and schedule equivalence. And so we looked at those concepts as well. So that's all I have on transaction processing. Thank you.